there, right? 1 week off. Thank goodness. So just FYI, the exam key for exam 3 is up and the blank exam is up. I hope to have those graded sometime this weekend. Actually, I haven't started grading them. I had another class, so I'll get those done this weekend. So our last unit or chapter deals with parametric and polar curves. So we'll look at parametric equations in 12.1, polar coordinates in 12.2, and then in 12.3 we'll do primarily derivatives, integrals, and arc length in polar coordinates. Parametric equation sort of fits in when we start thinking of polar coordinates. So we'll talk about it when we get there. But what we're discussing in 12.1 is the idea of a parametric equation. It just means that you've got an equation that's defined by a parameter instead of a single thing like we think of the input, the output. X is the input into some function, gives me some y value. That's pretty standard up to this point. What we're going to look at here is this other situation where we have our parameter t. So that's our parameter, or also the input. So we have our input as our parameter is t, and then our output, we really get two things. We get an x coordinate and a y coordinate. So that's our parametric description of functions. And we'll look at a bunch of different examples, but for example, we might have x of t being something like 2t plus 1, and y of t being something like t squared. And then there's a kind of a domain here. So you're given some value for t. T is in between 0 and 2, or something to that effect. So that's just an example of one specific parametric equation. We'll see many more in this section. And we don't there's not a whole lot of applications that we actually address with this, but there are many applications you can look at. I guess it depends on, for those of you that are in physics, you might have actually already done something to this effect, where you look at like projectile motion. So parametric equations are really good at describing projectile motion. Because if you think of projectile motion as having a vertical and a horizontal component, the vertical component is the parabola. So that's the the vertical component. The horizontal component is just linear, right? So we usually just look at it as time progresses on, what does this projectile do? But we could actually describe a projectile in terms of its horizontal component and its vertical component being quadratic and its horizontal component at the same time with a parameterized equation. The other advantage is, there's other types of advantage, but one of them could be like describing a circle. When we describe a circle in like the XY coordinate system, it's very discrete. It's like I plug one thing in and I get another thing out. But if we looked at that X and Y being described as a change in time or whatever, then if you're describing like the motion of a wheel, not only would we know where each point is at each given time, we could also see the motion in action. We could see the speed or calculate the speed and all that kind of stuff. You don't really get that if you just have this static plot of points in the XY coordinate system. It's impossible to tell where it's quote unquote starts, where it stops, what direction it's turning. You can get all of that stuff from a parametric type equation. So the terminology associated with how the parametric curve unfolds is they call it the positive orientation. So the direction in which the curve is generated as the parameter, usually t, so as t increases, is called the forward or the positive orientation. And depending on the situation, you might have, like with the circle, you might have the positive orientation, meaning the circle as we plot it unfolds in a clockwise motion or a counterclockwise motion. So positive orientation is just the direction in which it's generated. As for instance, t ranged from 0 to 2 here. How do we end up plotting these points? Do we end up plotting them like this, indicating that we have motion in this direction? Do we end up plotting the points like this, and so forth? So that direction is the positive orientation. And so what we'll do is look at a couple of examples where we're going to make a table of values for x and y, plot the table, or plot the points generated by the table, indicate the positive orientation, and then we'll eliminate a parameter from our parametric equation so we can obtain an equation of x and y that's a Cartesian equation, more familiar to us, and we'll describe the curve. So what we'll see is that if I take an equation like y equals to 2x plus 1, there are infinitely many parametric representations for the line, but they would all generate the line itself. They might unfold differently. In other words, their positive orientations might be different. Their starting points might be different, but we can have infinitely many representations for a single Cartesian graph. Sometimes it's tedious, sometimes it's not so difficult, but when we do have like a parametric representation, it is possible to eliminate the parameter t, so we just have x's and y's, or like translating it back into a more familiar setting. So we have x is cosine t and y is sine t. T ranges from 0 to 2 pi. So when we look at t ranging from 0 to 2 pi, and we'll just plot some of these values of t. And then we'll have our x and our y. So again, as t ranges from wherever to wherever, it's determining both an x coordinate and a y coordinate simultaneously. So the one input gives us two outputs. And then part B says plot the points. So we'll kind of do that as we go. All right, so t being 0, x coordinate is cosine of 0, y coordinate is sine of 0. So the starting value for t was 0. That gave us a point 1, 0. So we'll plot our point here and label it as the initial point. That way we know once we've have this plotted, we know where we started. And of course, we would have all values in between 0 and 2 pi. We just chose a few to plot. So t is pi over 2, cosine of pi over 2, cosine of pi over 2, sine of pi over 2 gives us the point 0, 1. So that's, somewhere in there. Cosine of pi, sine of pi. Negative 1, 0. cosine of 3 pi over 2, sine of 3 pi over 2. Get the point 0, negative 1. And then cosine of 2 pi, sine of 2 pi. We're back to our initial point, our starting point. So it's really not great. Let me scoot that down. Okay, so what do you think we get there? A circle, yeah. If you're not sure, you can plot points like, you know, when t is pi over 3, so forth. But in plotting these points and how t unfolds or increases, we see exactly how the circle unfolds, right? We have our initial point here, then we plotted this point here, so we went from there to there, and so forth. So here we would just say, it says indicate the positive orientation or the direction of increasing t. We would say that the positive orientation is counterclockwise. Most of the stuff we're not going to do by hand. I mean, it's some homework questions ask you to do this just so you're, you know, kind of starting out with baby steps. We can graph these various ways in Desmos. I think especially in the earlier stages where we want to see how things unfold, is you're basically going to plot that as an ordered pair where, you know, the x coordinate is whatever is defined as x in the parametric equation. Your y coordinate is whatever y is defined as, and if you put this bracket around it and say t is less than or equal to a, and generate a slider for a, then we can slide this and actually see it unfold. Otherwise, if we were just to plot by itself, if we were just to plot cosine t sine t, it's just going to generate the whole thing for us. So as an ordered pair, cosine t sine t. And t goes from 0 to 2 pi. So I mean, we can just graph them that way, but I think it's a little bit more clear if we graph it this way, and we can move a to see how it unfolds. So a would, you know, we would technically just go up to 2 pi, close to that. So that's kind of the idea, and you could imagine, depending on where t starts and stops, like if we stopped t at 4 pi, then we would actually get 2 circles. You wouldn't see 2 circles, but it would actually be traced out 2 circles. Okay, eliminate the parameter to obtain an equation in x and y. In other words, convert to a Cartesian equation. So our parametric equations rather, are this. And so when sines and cosines are involved, if we can isolate the sine and cosine of t, then all we have to do is square both sides. So this means that x squared is cosine squared, y squared is sine squared. And we know when we add sine squared and cosine squared together, we get 1. So that's pretty much it. That's our, I should have wrote it the other way, but this is y squared plus x squared is equal to 1, which we recognize as a circle with a center 0, 0, radius of 1. So that's our description in part D, or describing the curve in part D. Circle, center, 0, 0, with a radius of 1. And I guess we could go a little bit further. We could say it's a circle, center 0, 0, radius 1. We could also describe where the initial point was. Initial point was 1, 0, and we did describe in part B the positive orientation unfolds in the counterclockwise direction. So do y'all have any questions about that? Okay. So we may not actually work all of these examples in this section, but we'll do enough to where we have a decent idea of what's happening. So, you know, this example and the second example here are pretty similar. I think the second example is a little bit more involved. So we'll do this one with the hopes that it'll kind of take care of the first example. So we have x is t squared plus t and y is 2t minus 1 for t between -2 and 1. Again, we're going to make a table of values and plot the points. So I don't know, I always do this. I don't know that it's a standard kind of thing, but just to kind of compartmentalize those inputs, outputs. All right, so ranging from -2 to +1. And since t starts out at -2, whatever we get here, this is our initial point. For t equals -2. So we have the x-coordinate is -2 squared plus 2, and y is 2t minus 1. I don't know, how many other points do we want to look at? It might not be evident as to how many we should look at. But we definitely have to go from -2 to 1. Just 2 more.
Stick with the whole numbers.
Okay, so -1 and 0. All right, let's use those for now. And you know, if we end up with these 4 points and still no clear idea as to what it is, then we'll just plug in more. Okay. So when t is -2, x is 2, and y is -5. So that's our initial point, 2, -5. I'll plug this in. When x is -1, or sorry, t is -1, x is 0, y is -3. So it's really not our second point, it's just the second point that we're plotting. So we have 0, -3. X is 0, sorry, t is 0, x is 0, and y is -1. 0, -1. And when t is 1, x is 2, y is 1. Yeah, 2, 1. So can we tell what that's going to be? Uh-huh. Maybe, yeah. I think we could speculate it'd be a lot of things at this point. Definitely not a function, right? We've got these 2 points stacked on top of each other. So maybe we should choose some other points. We're not quite sure. So a couple of other things we want to try plugging in.
Negative a half. Negative 1/2.
T is negative 1/2, and then we'll see what happens when we plug in a half, I guess. Okay, so negative 1/2, x was t squared plus t. So we've got, what is that, 1/4 plus a half? X is 1/4 plus a half. Y is negative half times 2. So negative 1 minus 1. 3/4 negative 2.
Wouldn't it be, yeah, that's what, negative anywhere?
For which one?
Your x value, 'cause it's plus t. Could be
Oh,
negative.
yeah, right, thanks. So negative 1/4. Common negative 2. Negative 1/4, negative 2. So I don't know, it's not going to be to scale, but here we have this point here. Fourth plus a half for t equals to 1/2. 1/2 squared plus 1/2. And 1 minus 1. 3/4 comma 0. What's that point? So is that helping? So, like, I don't know, maybe my drawing's a little too sloppy, but we have this point here, this point here, this point here, this point here, this point here. Those are in line. This point here. You know, we plot another point, it's going to be here, another point here. That's not good. I'm trying to use this without the grids. There's our initial point. Still maybe plot more points, or that's why we have part C, eliminate a parameter, so we can determine what this looks like in terms of x or y. So we'll stop there with the graph because I think it's kind of redundant at this point. But we know where we start at this red point, and we stopped here when t was positive 1. So this is our ending point. 2, 1. So we know whatever it is, where it starts and stops at least. So let's look at part C so we can try to determine what this actually is. So we had x was t squared plus t, and y was 2t minus 1. So the idea is just to eliminate the parameter t from either one of these equations, what that entails is to take one of those equations, x or y, solve for t, and then plug it into the other equation. So we just pick which one looks easiest to solve for t. Clearly, the second equation. So we're going to solve y equals to 2t minus 1 for t. And so we have y plus 1 over 2 is t. then plug this into the equation for x. That way we have a single equation involving x and y. So we have x is t squared, or y plus 1 over 2 squared, plus t, again, y plus 1 over 2. All right, so what we have, y squared plus 2y plus 1 all over 4 plus y plus 1 all over 2 y squared plus 2y plus 1 over 4, and then our y plus 1 over 2 is 2y plus 2 all over 4. Just combine like terms at that point. X is, we've got a y squared over 4, or 1/4 y squared. We're going to have 4y over 4. And we're going to have 3 over 4. So maybe that's not terribly helpful because we ended up with an equation as x equals, we're accustomed to seeing y equals. But I think it does hopefully shed insight onto what our graph was actually developing into. What is it? Yeah, it's opening to the right. It's a parabola, but it opens to the right instead of up. And honestly, if we solve for t and x and then plug that into y, we would have y equals 2. But it's still not. We can do that, but it's still not going to look like a nice equation. It might be more recognizable, but we can certainly walk through that process. Or solve x. Solve this for t. How do we solve that for t? So the variable we're solving for is t. Clearly it's t squared plus t. So that's quadratic in t. Again, if this were all 0, we just factor out a t, set both factors equal to 0. That's not the case. So we're going to have to look at it as 0 equals to t squared plus t minus x. We're going to have to look at that as our quadratic. This is quadratic with our a being 1, b is 1, and c as that number, negative x. So it's a little more work to solve for x, but when we plug it in for y, at least we're in a more familiar y equals 2 situation. So we have that t is equal to the negative b plus or minus the square root of b squared minus 4 times a times c. All over 2 times a. So we have in our radical, we have 1 plus 4x the radical all over 2. And that's what t is. So solve the x equation for t, we get this, and now we're going to plug this t back into our y. So y was what, a 2t minus 1, or 2 times t minus 1. And so that just gives us the 2's divide out. We've got a -1 and a -1, so we have, I guess we can write it as -2 plus or minus root 1 plus 4x for y. And so there's a different yet equivalent representation for that quadratic in y. So of course the positive root gives us one of the arches up to the vertex, and then from the vertex below is the negative root. So I don't know, at least with the expression we had for x as being that quadratic in y, we could determine where the vertex of the quadratic was. But either representation is fine. I think the main point of part C is just to get something that you recognize as Cartesian representation. Okay, do y'all have any questions on this? So with this expression here that we had for x, we could find the vertex. We just do the negative b over 2a. And evaluate, I don't know what we're going to call this, x. Just for our notation here, call it g of y. And then we'll evaluate g at negative b over 2a. What is the vertex? Might not be as clear as in this equation we had for y, like what the vertex was. And we could plot both of those for sure, though. So that's what we've got. We've got this. Go back up to the graph. We've got this as a quadratic. Initial point here. So we're unfolding in that direction. A nicer graph there. Again, if we sort of see our initial point, then we can advance this, see how it unfolds. I don't know that will actually tell us any points, but anyways, stick that in our notes.
Let's try that again. Thanks.
All right, so that's kind of the basic idea of, just looking at a couple of these. We're going to look at, equations for circles. Some other examples are just what we did here in Part C, where we eliminate a parameter and end up graphing the parametric equation. Then we'll look at derivatives, how to take a derivative in this kind of setting, and arc length, how to find an arc length with a parameterized version. So we kind of mentioned this before, but if we had a Cartesian equation that's 2x minus 12 equals to y, many infinite number of representations for a parametric equation. So one of them could be that, we're just maybe sticking with ones that are more obvious, but if x were t and y were 2t minus 12, that would be 1. And then so just from that setup, we could do whatever we want. We could say it's kind of the same. X is, if x were t squared, we could say that y is 2t squared minus 12. Another representation, and so forth. So that, these are a little, I think, pretty straightforward. And then whatever x is, we're just going to put that in for t. If x were 2t plus 4, then we could say y is 2 times 2t plus 4 minus 12, and so forth. Again, those are probably a lot more obvious, but they aren't unique. The initial point could change, the positive orientation might change, but the fact of the matter is that they're all drawing out the line 2x minus 12. So circles with a parametric representation. This is our Cartesian situation. And you might remember, or you might not, that the various A, B, C's, and D's do different things to the graph of either sine or cosine. Just a couple to revisit here. This A affected the what? For sine or cosine? Yeah, and like in what sense? Like this way or this way?
Vertical.
Yeah, vertical. So that it's like a vertical transformation, right? We're stretching it or shrinking it in the vertical direction. So this was the amplitude. What about B? So like, what if it were yeah, it's like compression, horizontal effect. So what that affects is the period. Remember, for sine and cosine, the period is 2 pi over the absolute value of B. C was the phase shift, horizontal, left, right, and D was the D is up or down translation. So it really A, B, and D we're going to focus on when we look at a parametric equation for a circle. We don't deal with ones that are with a minus c in there. Do I have that written down? I guess I don't. Okay, so I don't have that. It's parametric. When you write x or x of t, I'm going to start out with a times cosine of b times t plus d. And y is going to be capital A sine of bt plus, we'll just call it lowercase d. So notice here, like in the same situation, we have kind of two of those Cartesian things applied to both outputs, the x and the y now. The A is still affecting, in the x direction, and then the y direction for sine. The B still affects the period because it's with the argument of the sine or the cosine, and the D is still up or down, but in the sense that it's up or down with respect to the y coordinate, and it's now left or right with respect to the x coordinate. So this type of situation, what we have is this is a circle with a radius equals to the magnitude of A the period, and here we can think about the period as just how much of the circle actually gets graphed. It's still, for sine and cosine, 2 pi over absolute b. And the center of the circle is capital D, lowercase d. So honestly, it's something you should recognize. If you're not able to like readily recognize that's a circle, maybe when we look at eliminating the parameter t, you should remember that one or the other, or both, preferably both. So if x is the cosine and the y is the sine, in this setting, the positive orientation, so let's just say if capital B is positive, the positive orientation is counterclockwise. And if B is negative, it's counterclockwise. So really, that's kind of the most generic way we could say that. Depending on where t ranges from, would determine where the initial point is. So we can't really say anything about that in general. So oddly enough, well, maybe not oddly enough, but if we swap the fact that x is a sine and y is a cosine, it's still a circle, the same characteristics. The only thing that changes is the orientation, what the positive orientation is. So if we have x is a sine bt plus d, and y is cosine. It's the same as above, but the orientation is the other way around. If b is positive, the positive orientation is clockwise, and for b negative, it's counterclockwise. Well, I didn't put an example of in our notes like word sine, cosine, but we can certainly look at that once we get to it. Okay, again, if you don't remember, then hopefully like when we convert, that process is simple enough to remember. Like if I don't know what I'm looking at, then I can convert into x and y, and then from there I can clearly see what type of thing I'm dealing with. Do y'all need some more time to copy that down? Okay, so this example, t is 0 to 2 pi, and we have x is 12 cosine 2t, and y is sine 12 sine of 2t, rather. So what is this? It's a circle. The center is at 0, 0, right? Because we can look at it like this. Their center is 0, 0. What determines the radius? Yeah, the A, the 12. So one way we could just know that, right, and say, okay, well, this is a circle, radius of 12, center at the origin. And then there's other things we can describe depending on what it wants us to describe. How much of the circle is generated with x and y as t ranges from 0 to 2 pi? 2 circles. What do y'all think? So the period, which is how much of the circle, is 2 pi over b. Our b is 2. So we have one, basically it tells us that a full circle is generated every pi units, right? But t is going from 0 to 2 pi. So you get 2 circles. Circles generated here of radius 12, center at 0, 0. Does that make sense? Another way you can look at that pretty quickly is to say that, well, if t is 0, if t is equal to 0, then I have cosine of the argument 0 and sine of 0. And when t is 2 pi, we're just going off of where t starts and stops. And if t is 2 pi, we have the cosine of 4 pi and the sine of 4 pi. So I mean, that's another way of like explicitly seeing what t ranges from. T ranges from 0, or sorry, the argument rather, t ranges from 0 to 2 pi. We're plotting the cosine of 0 and ending with the cosine of pi over 4, or sine of 0 ending with the sine of pi over 4, right? So you get 2 circles there, from 0 to pi over 2, and then from pi over 2 to pi over 4 is 2 circles. I don't know if that's a helpful way to look at it or not, but you can always do that too. What is the orientation of the circle? Yeah, counterclockwise, positive orientation. Is counterclockwise since b is equal to 2, which is positive. Okay. I didn't really ask for like the initial point or anything, so we'll just verify this, and then if I still have space, we'll look at how we convert or eliminate t from this. So I have 12 cosine 2t. So there's our initial point. So that's pretty much 2 pi right there. And we have to go out to 4 pi, whatever that is. I think we can go far enough. But anyways, you're not going to be able to see the circle tracing here in this software either, so just got to know that it's traversed twice. Okay, so the way we can convert that is the way we've converted the other few that, or the other one, I guess. Have this. So since x is 12 cosine of 2t, again, what we want to do is isolate the sine and the cosine. So we have x over 12 is cosine 2t, and y over 12 is the sine of 2t. And then once we have those isolated, we'll just square both sides. So you have x squared over 144 plus y squared over 144. X squared plus y squared, or sorry, this side squared, it gives us cosine squared 2t, sine squared 2t, and we know that's equal to 1. So then we just multiply both sides through by 144, so we have x squared plus y squared equals to 144. So that's always the trick, or the procedure when we're converting a parametric equation that involves sines and cosines into x and y. Basically, you solve for sine and cosine and then square both sides. Okay. Any questions on this? Okay, what about example 4? certainly has the format of a circle. So again, the radius is 12, determined by the, I guess, A here. It's 12. What's the center?
-1,
-1, 3. Positive orientation,
counterclockwise.
counterclockwise again. And then how much of the circle do we get?
1.5.
Half? Does everybody agree? Do we get half a circle? Or something different?
Yeah.
Half a circle. And so we range from 0 to, or sorry, t ranges from 0 to pi over 2. So we can think about it, I guess, again, two ways. The period here is 2 pi over b. The period is pi, one full circle every pi units. But t is only going from 0 to pi halves, so half a circle. Or again, oops, we can just think about the t being input into sine and cosine. 2 times 0 is 0, so we'd have sine cosine of 0. And then we would have at the end sine cosine of 2 times pi over 2, or pi. 0 to pi is where the argument goes. So half a circle. Which half really depends on the initial point, right? Where that starts, we're generating half of it in the counterclockwise direction. Convert, oftentimes that just, they'll say eliminate a parameter, which is the same thing as converted into Cartesian. So again, all we're going to do there is solve for the cosine of 2t and the sine of 2t. So we have x plus 1 divided by the 12 is the cosine of 2t. Similar thing for y minus 3 over 12 is sine of 2t. So then squaring both sides. X, y. Yeah, we'll do cosine first. From that relationship, that means x plus 1 over 12 quantity squared plus the quantity y minus 3 over 12. This quantity squared equals 1. Everybody all right with that? Sort of standard conversion here. Again, we have the quantity x plus 1 squared plus y minus 3 squared equals 1.4. So circle radius 12, centers at negative 1, 3. So even in this situation, like it's weird at first to look at the circle, but it's fairly natural here. I mean, you don't, like in the Cartesian system, it was, well, this was a shift to the left 1 unit, and this was a shift down 3 units, right? But here, when we look at the parameterization, it is as it is, right? The x is shifted negative 1, and the y is shifted up 3. So it's not, maybe in some sense, a little more intuitive than it is initially in the Cartesian sense. I don't know. But that result verifies with what we said about the equation, the parametric equation. Do y'all have any questions on that? I don't know why it keeps doing that.
What kind of stuff would you ask on, like, an exam? Or this kind of stuff, would you just say, like, what is the radius, what is the center, kind of basic?
Yeah,
like
just
little
kind
points?
of, yeah, pretty much. Like if something like that shows up, yeah. There's, you know.
You can make it big points too, I mean, it could be like, 30 points for, tell me the radius, kind of thing.
Yeah, sure. Yeah, so I think more so the derivative stuff and the arc length stuff. But I mean, this certainly would be, I think, a reasonable test question where it's like, what does this parametric equation represent? Eliminate the parameter to show it in a Cartesian. Yeah, same kind of thing we're doing here. Yeah. Oh, wrong one. All right, it's kind of a similar thing here with the circle. Remember we said that the radius of the circle is the absolute value of A, so it doesn't matter if the number here is negative or not. The radius is 3. The center, we've got our x at 1 and our y at 2. And how much of the circle is generated in this one? One full circle, yeah. Here b is 4 pi. So we have the period is 2 pi over 4 pi, 1/2. So one full circle generated every half, I guess, increment, if you will. One full circle generated here. Positive orientation again, since b is 4 pi. Positive orientation is counterclockwise. And the conversion is very similar to the last problem we just did. So those are our circles in parametric form. Do y'all have any questions on any of that? Hopefully that's somewhat straightforward. That's not terribly involved. Other types of problems have us finding a parametric equation for specific information. The thing is there could be, you know, what you come up with that works in this situation, someone else might have something different, because there are infinitely many representations here. So a circle with a center of 2, -4 and a radius of 3/2, generated counterclockwise with an initial point of 7/2, -4. So I would sort of fit in the information that's pretty clear as far as the center and the radius, and then fine tune it if need be to get that initial point. So like if we start out and say, well, x is something involving cosine and y is something involving sine, what would accompany our x being cosine? What would be there with that?
The 3/2.
The 3/2 would be here,
Yeah.
multiplying that. Same thing for the sine, because that's our radius. And then so just, you know, start out with a basic argument of t, and then you can modify that if it doesn't line up with the initial point. The 3/2 cosine t needs a +2 to be centered at 2 for the x coordinate, and a -4 to be centered -2, -4. So I mean, that's initially what we would come up with as maybe the most obvious choice, and then we'll just check the initial point. Before we actually check the initial point, what do we need?
What to plug in, like the range.
Yeah, for what?
The range for t.
For t, yeah. So where do we want t to range from?
Like 0 to 2 pi.
Okay, let's try 0 to 2 pi. So the initial point should be 7/2 -4 when t is equal to 0. And so that's basically what we're checking. If I put 0 into what I have come up with for x and y, do I get 7/2 -4? So I have 3/2 plus 2, that's 7/2. And we have 0 minus 4. So that does work. So you can see, you know, all the things you could vary here. I mean, the 3/2, the 2, and the -4 have to really be where they are. But we could modify the argument of sine and cosine, at which point we could modify where t ranges from. Could also still come up with something that's 7/2 -4 when t is 0. But since we found this one, I think that's good enough. Another one, I'll write out another one that happens to work here, but isn't as obvious, just so we can see, you know, alternative representation. So that's one thing that works, another one that works, I only came up with one other one. But if we said that x was -3/2, cosine t plus 2, and y was +3/2, sine t minus 4, from t ranging from pi to 3 pi also works. So there's many things we could modify there. I wouldn't try to think about it too much as far as getting clever with it. Just whatever seems obvious and modify from there. Okay. So a few more examples of converting or eliminating the parameter. I think we'll skip that one because we've done many of those here. Let's see how many more we have. 1, 2. Maybe we can look at the ones that don't involve the sines and cosines. Eliminate the parameter and graph it. So then, from here, with sines and cosines, it's straightforward. Square both sides, set it equal to 1. With other versions, like what we have here, it's your choice whether you want to solve for x or whether you want to solve for t in x or t in y. So which one do we want to solve for here, x or y for t?
X.
Okay, solve for t in this one. So we have t is x plus 3, and then we'll plug that into our y. For t. So we can have y as 2 times x plus 3 plus 4. Or we have y as 2x plus 10. So we can see that represents a line, but it's not the full line because t only ranges from 0 to 2, so we get a partial line, if you will. So graphing it just involves t equals to 0. So we have x is -3 and y is 4. So this is our initial point at -3, 4. And then since we know it's a line, let's just draw or graph the terminal point and then connect them. We know where it starts, we know where it stops, we know it's a line. When t is 2, we have -1 and 8. So somewhere up here, -1, 8. That's our terminal point. So we just have that line segment there. Easy enough? So we would, the positive orientations for like lines and stuff, it's a little bit harder to describe. So it probably won't be asked, but I mean, just something descriptive enough to say that it moves from left to right. So as t unfolds from 0 to 2, the line increases from, I don't know, -3 to -1. And so, yeah, usually if you take the equation for x, solve for t, and plug that in for y, then you're going to end up with an expression for y, as we're more familiar with, I think, than x equals to y. So this example just illustrates the fact that t doesn't have to be restricted. We can let it range from negative infinity to positive infinity. But and then taking this equation, solving for t and x, and then plugging that into y. T squared, which is 4x plus 4 over 2 squared. So what are we going to get there?
Quadratic?
Yeah, quadratic. It's x squared. So the 4's cancel out, and we just have y is x plus 4 quantity squared. So that's just our quadratic that's shifted to the left 4 units. And so which way would our arrows point? Would they be from right to left or from left to right?
Not sure, right?
Yeah, so if this were negative infinity, just think about plugging in a large negative number. If t is large and negative, x is large and negative. No initial, no terminal. Okay. Any questions on that one? What about example 10? Is it a circle? How do we know it's not a circle?
Different.
Yeah, the A's are different. So let's see what this is. Same procedure. We wanna say that x over 2 is cosine t, and y over 3 is sine t. So then, again, squaring both sides, we have cosine squared plus sine squared is equal to 1. In other words, x over 2 squared plus y over 3 squared is equal to 1. So what's that? It's probably been a while. Ellipse, yeah. It's an ellipse. How do we determine what the ellipse looks like?
Isn't it the square root of the denominator? The axis length?
Is the axis lengths, right? Yep. So the orientation of an ellipse, what's the center, first of all? The center of the ellipse would be at 0, 0, yeah, because it's not x and y minus anything. Center at 0, 0. The longer axis is determined by the variable over the largest number. So 9's the largest number. The y is the largest or the longer axis in the y direction. So our major axis, they call it, major axis is vertical, which just means that the ellipse is more elongated in the y direction than it is in the x direction. So we've got just a quick sketch. The square roots of our denominator are the axis lengths. So our major axis has a length of 6. And our minor axis has a length 2. So that's basically the boundary of the ellipse. It's less exaggerated like that if we were to graph it, because the 2 and 3 are really closer together, but it would almost look like a circle, but it's not. So if the capital A's are different, like one's A and the other's lowercase a, you're going to have an ellipse. And T ranges from, so that's the graph of our Cartesian, but then we have to come back and say, okay, well, T ranges from 0 to pi. So do we generate the full ellipse? Let's find the initial point first. T is 0, so our initial point would be 2, 0. So there's our initial point. If T ranges from
It's just half of it, right?
0 to pi, yeah. If T ranges from 0 to pi, then again, what we're looking at is the cosine of 0, sine of 0, and the cosine of, at the end, cosine of pi, sine of pi. So it's just going to give us half of the ellipse. So really we have our initial point. All we've got to do if we're not sure which half it is just to determine where the terminal point is. So when T is equal to pi, what is x and what is y? So when T is equal to pi, 2 cosine, 3 sine. So we'll kind of group these together. And then once we have, our terminal point might give us a better idea which half. Maybe not, I don't know. Depends on how we look at it, I suppose. So at cosine of pi times 3. And then
That should be times 2.
sine of, what?
The cosine was times 2,
Oh.
pi was times, or the
Alright.
sine was times 3.
Okay, thanks. So negative 2, 0. So here's where we stop. So which half? Didn't really help. Could be the bottom, could be the top. the top, yeah.
Because it's counterclockwise?
Yeah, because the positive orientation in that sense doesn't change. X is still cosine and y is still sine. So it's analogous to how that circle situation behaves. Okay, so we have that thing. I'm just gonna go ahead and erase this piece. All right.
In this case, when would it be drawn the other direction, or the lower?
So like if it were in the well, if we had the if this thing were oriented positively in the clockwise direction,
Yeah.
we would have a cosine of negative t and a sine of negative t.
Okay.
Would change our initial point over here, and then we would orient that way.
Okay.
Um,
Gotcha.
yeah, so that's how that would be affected in that situation. Any other questions? What's 11?
Circle.
That's a circle. Skip that one. Okay, so here, eliminate the parameter from x is t squared, y is ln t, where t is larger than 0. So just to obtain y equals, if you wanna always obtain a y equals in that situation, just like we've been doing, we have to solve for x for t. And then plug that in for y. So what is t equal to?
Square root of x.
Yeah, just the square root of x, not the positive and negative square root of x, right?
It's above 0.
Because t is above 0, right? So we just have a single representation for t as the square root of x, and then we're plugging that in to y. So y is the natural log of the square root of x. And I think it might be maybe a little bit more beneficial for graphing to say that's the same thing as 1/2 times the natural log of x. So all we've got is the natural log function. We've divided it by 2, so we've compressed it in the vertical sense by a factor of 2. So there's our graph. So what part of that graph do we get? Do we get all of that graph, a portion of that graph, or what? All of it? Do y'all agree?
Yeah.
All of it? Because the domain here for this function agrees with the domain of the parametric equation. And we start somewhere down here. But it's, like we probably, once we have the graph, we need to refine that in the sense of what our parametric graph actually looks like. So here's 1/2 ln x, but t starts out at what was it? Larger than 0, right? So and then it progresses onwards. So then we should actually have the same graph here, but these arrows look like this. Just be mindful when you're looking at the Cartesian representation that you've got to then look at what it came from to determine if there's any restrictions on the actual Cartesian graph. So this is our actual graph here. Does that make sense? Do you have any questions about this? Okay. All right then, so once we've seen like these functions represented as a parametric equation, then the standard stuff as far as calculus goes, what's the derivative at a point, what's the arc length, what's the area, like we can do all of that stuff with parametric representations. We're going to focus on derivatives and arc lengths. When you get into Calc 3, you'll parameterize a few things, and that's going to, in theory, it makes things easier to deal with, but you will be integrating with respect to the parameter, derivative with respect to the parameter, and it's all, I think, pretty logical as far as how that's done. So like in the parametric sense, the derivative of y with respect to x is the same thing as the derivative of y with respect to t over the derivative of x with respect to t. So we can think about that as g prime over f prime if you want. I think it's maybe more explicit to say it's just y prime over x prime, where t is our independent variable. So the derivative of y with respect to t over the derivative of x with respect to t, it's a very natural thing to follow this. Okay, so the parametric equation given as follows: root t for x and 2t for y, and evaluated at t equals 4. So we're taking that parametric equation, whatever it looks like, and we're saying when at the place where t is equal to 4, whatever that ordered pair is, what is the actual slope of that curve generated here? So the derivative, we're still labeling as dy over dx, although it is really dy over dt, dx over dx over dt. I mean, we can just see that from an algebraic standpoint. If we divide those two, it is dy dx, or y prime over x prime. So we just have the derivative of y with respect to t over the derivative of x with respect to t. So the derivative here with this parametric is just 4 root t. And so then we want to take the derivative and evaluate it at 4. So let me just, sometimes the notation you see is kind of the same as the notation you see with the antiderivative stuff. So, what we want to do is evaluate this right here. So that's a notation that they use. We're evaluating this at 4, sorry. That's the slope of the tangent line on that parametric equation when t is 4. So when t is 4, we have the point 28. That's it. That's that steepness. The steepness of that curve at that point is 8. Has nothing to do with the y value, of course. Y'all have any questions on that? Okay. The other example we're going to look at has to do with, because with these parametric equations you can get pretty elaborate shapes. So we're going to look at the next example where we're finding vertical tangent lines and horizontal tangent lines. Or not. I don't know if that disappeared or not. All right, well, maybe we'll come back to that. But arc lengths are defined as the integral from a to b root f prime squared plus g prime squared, where f prime, or where f rather is corresponding to the x and g is corresponding to the y. So we can think of this again as just x prime with respect to t squared plus y prime squared. Under the radical. So find the arc length of the asteroid. We'll go ahead and graph this. Like in polar coordinates and oftentimes in parametric, if you can utilize symmetry, it can simplify these problems a great deal. So let's go ahead and look at the graph for this. I don't know if it likes that or not. Doesn't like that. We're going to put that in our notes. You'll see that we'd be able to do it without the graph, but knowing that the graph has symmetry and being able to utilize that symmetry is going to make this so much easier. So we want to find the arc length of the entire thing. And so what we have to do is we have to find x prime square and then y prime and square it. Add those together underneath the radical. So the derivative of x with respect to t would give us what? Okay. So the cosine would be square because the power we subtract 1. Cosine t, and then take the derivative of cosine. So -3 cosine squared sine. And then we have to square this so that we have 9 cosine to the 4th sine squared. And do the same thing with our y. Y prime is 3 sine squared cosine. Chain rule, and then squaring that squared. So we have to add those two derivatives squared under the radical. We're going from 0 to 2 pi. It's the square root of all of this stuff added together. So 9 cosine to the 4th t sine squared plus 9 sine to the 4th cosine squared dt. So we can simplify this a bit just by factoring out the greatest common factor. And so we'll factor out a 9 cosine squared and a sine squared. So we're left with cosine squared after we factor that out, sine t, sine plus sine squared. And all of that's still under the radical. So what is that? What do we have now? What we have now, rather, what does it simplify to? 3? For the 9, yeah, square root of 9 is 3, so we get a constant there.
3 cosine t sine t.
Okay.
Times 1.
Times 1, yeah, because this is just 1. So the issue with this is that it's not actually 3 cosine sine, right? It's 3 times the integral from 0 to 2 pi. And let's just write this out here as this step. So if we say that's equivalent to the integral from 0 to 2 pi of just cosine times sine, that's not correct. What's wrong with that? Saying that they're equal.
The dt, isn't that?
Oh yeah, dt. Yeah, that's what's wrong with it. What else is wrong with it? What else is wrong with it? It's not that we don't have any middle terms because we're not squaring like a quantity that's added or subtracted. This is the same thing that would be wrong with saying that not knowing where x is, the square root of x squared is equal to x. It's the same thing that's wrong with that. Could be positive or negative, right? So it's the absolute value of cosine times sine. Now the reason it's the absolute value, again, because in the interval from 0 to 2 pi, cosine and sine are positive and negative, right? So either we're going to have to break this thing up into 4 different integrals to where we know, like, over here, in the first quadrant, cosine and sine are both positive. In the third quadrant, both of them are negative, right? And so we sort of encountered that when we were dealing with, way back in the very beginning with displacement versus distance traveled, right? So, that's one way to look at it is like this, but if we utilize symmetry, then we don't have to worry about the absolute value component here with that. So on the interval from 0 to pi over 2, cosine and sine are positive. Which means that if we looked at the integral from 0 to pi over 2, we don't have to say it's the absolute value of cosine times sine. Since they're both positive, then we just say it's cosine times sine. Right? We still have the 3 there because that's just there. But, sorry, pi over 2. If we go from 0 to pi over 2, what else do we have to do to this integral? Yeah, multiply it by 4. Because if we only go from 0 to pi over 2, we're only getting this arc length here. So all we're going to do is just utilize symmetry and say, well, there's 4 pieces that are exactly like that. So not only does it simplify the bounds to use symmetry in this case, but oftentimes it sort of, we can sort of avoid these, difficult situations where we'd have to break something up. Maybe you have to integrate across a place where the integrand is 0 on, like if we went from like pi over 2 to pi. Depending on the curve, there could be something funky happening in between pi over 2 and pi. And so we say, well, we'll just ignore that. If it has symmetry, we'll just look at the easy part and then multiply that by 2 or by 4 or whatever. So we have to multiply this by 4. That's not a good color there. We have to multiply our original integral from 0 to pi over 2 by 4 if we're going to only go from 0 to pi, or 0 to 2 pi rather. We have to multiply by 4 if we're only going from 0 to pi over 2. Then we don't have to deal with absolute values, and it's a pretty straightforward thing to deal with. So we've got 12 times the integral from 0 to pi over 2, cosine t, sine t with respect to t. So how do we integrate that? You can integrate by parts, yep. Or what's the derivative of sine? Cosine. So we see that this function's derivative is right here. So we have 12 times the integral of u du, and u goes from
Squared divided by 2.
yeah. What are the bounds on u though?
Can we just switch it back?
You can switch it back. Yeah, but notice if t is 0, u is 0. If t is pi over 2, u is sine of pi over 2. So I don't know, I personally like doing that. If you like to switch it back after, that's totally fine too.
I guess it depends on how far you're wanting us to go.
Yeah, I mean, we're going to evaluate it completely anyways, so it doesn't matter. If you want to find the antiderivative of u, resubstitute cosine sine, and evaluate the antiderivative of, it's going to be cosine sine squared over 2 from 0 to pi over 2, then you can do that as well. I think 0 and 1 are easier to deal with, but at the end it doesn't really matter. So we've got 6 u squared from 0 to 1. Which is 1 times 6, which is 6. So the arc length L is equal to 6. So you can see that, you know, these, even though we can do this, in a lot of instances you could end up with like an even more difficult integral than what we've seen in chapter, what was it, chapters 8 and 9 or whatever? No, chapter 8. So I'm not claiming that it's any easier, I'm just claiming that it's doable. Do y'all have any questions on that? All right. I know it's virtually impossible to do homework over the break, but if you can try to stay up with this stuff, because when we come back, we only have 2 classes left. So we got to finish 12-2, 12-3, and review for the final. So would y'all rather try to cram all that stuff in when we come back, or we want to keep going?
I mean, we have 10 minutes, so I don't know how much we can cram into 10 minutes anyway.
Either way, there's cramming needs to be had.
Yeah, exactly. You can cram later.
Okay. Is everybody okay with that?
Procrastination is the key.
Seems everyone's fine with that. All right. Y'all have a good break. I'll see you.